But the action potential, no matter how long you send the action potential to, it will never reduce the size. You generate action potential at this location, and at the end, you will receive exactly the same size, frequency of the action potential you generate at the beginning. So that is how the neuron send signals. And make sure that you send small signals, control your muscle, not because the muscle is far away from your neuron body and it receives less signal. It won't happen. As long as it travels as action potential, those long distance communication, it will just go through the whole track, go through the whole axon, or sometimes muscle cell. Those places will receive the action potential and spread as action potential. The signal do not decay. That is the difference between action potential and a graded potential. So the action potential is a brief reversal of a membrane potential. So it always go to the zero, go to the positive part. So from the minus 70 here, you get, and you just receive a signal once it reaches the threshold. Here's the threshold. As long as the potential change above the threshold, it will generate all the rest of action potential, which can reach about 100 millivolts. So that is an action potential, and that is one action potential. It will not decay no matter how long this action potential is sent to, but graded potential normally will decay. So the action potential can travel in a long distance, but the graded potential will just decay to zero as long as the distance is long enough. Before we talk about how the action potential is generated, let's talk about the gated ion channel first. So for those sodium ion channels on the neurons, those sodium ion channels have a 2 voltage sensitive gate. Remember those voltage sensitive gate? That's the one that will control the open or close of those ion channels. And on one sodium ion channel, there are 2 different gates. So one is activation gate. It's normally closed. And once the depolarization reach certain level, and those gates will open. That's the activation gate. And the other is inactivation gate. So those gates normally are open at rest, which you see is here. It's open at rest. Those are round, small ball here block this channel, and at the beginning, at the resting stage, we don't have this ball blockage, and once it reaches certain threshold, then those ball will close and close the whole door. So what you get is a one gated channel, that's one pair, open at a certain threshold, and the other one close at a certain level of the membrane potential. Keep that in mind, and let's see next one. The potassium channel have one voltage sensitive gate, so it will just open as long as a membrane potential reach the threshold, reach certain level. So that is potassium channel. It's closed at rest, open once the cells start to depolarize. We said the action potential is a brief change in membrane potential, and in fact is a result of the open and closing of the sodium and potassium ion channels on the cell membrane. So what we see here, this is always the action potential, just look like this. So during this curve, start from minus 70 millivolts on the cell membrane. It is a resting membrane potential at the first stage, and then it will start to depolarize first because things go up, which is depolarizing, and the cell membrane potential reached positive, and then it will go back, which we call repolarization. Remember the resting, we call it polarized. So depolarization, repolarization, which is polarized again. And normally it will although it will reach the resting membrane potential, but it will go a little bit deeper. So we call the last stage is a hyperpolarization. So those four step of action potential is a result of a different ion channel open and close. The first stage, the resting membrane potential, which have no stimulus there, and the gated sodium and the potassium channel are closed. Here we are talking about those gated channel, which once they opened, those sodium ions and potassium ions will just go across the cell membrane according to the electrical and chemical gradient. So at this stage, only the leakage channel for sodium and also potassiums are open. So that is a resting membrane potential, and that maintain the resting membrane potential at the -70, around the -70. Then if there's a local stimulus, it's normally a local current, form of a current, that depolarize the cell. And once it gets depolarized, it will open voltage-gated sodium channel first. So it's a sodium first. And once the sodium channel opened, because there are a lot of sodium outside and just a little bit sodium ions inside, so the sodium will rush into the cell. Please make sure you find those directions. The sodium go into the cell once the sodium ions open. So the sodium ions influx will cause more depolarized inside the cell. Because positive go in, then the negative inside kind of go to the zero. So that is how the peak, the rising part of the action potential formed. That's a depolarization. And here you see there's a threshold, this line here. And once those sodium ion channel open and make those membrane potential reach the threshold, at that time there's a positive feedback form and make those peaks suddenly rise. As long as the membrane potential reach the threshold, the action potential will be generated. And on the other hand, if the change on those membrane potential didn't reach the threshold, the action potential cannot be generated, because at this point there's more, or we see all the sodium ion channels are open. So at that time you cannot stop it. Once the action potential reaches the peak at about plus 30, then positive 30, at that time those sodium channels will slowly inactive, because there's another gate block the sodium ion channel. So at that time the sodium ion channel closed, and remember we have more potassium inside and potassium out than the outside. So at that time those potassium ions will come in to change the action potential. So that time the potassium channel open. So since there's more potassium inside the cell, less potassium outside the cell. Once the potassium channel open, so the direction of potassium is to flow out, the exit. So potassium open and potassium exit the cell, and that will make the inside of the cell become negative. Because the positive charge go out, then the inside become negative. Okay, so which give you the third step, which is a repolarization, because it come back to the polarization state again, so repolarization. So let's see, the resting membrane potential is about here, and those we call polarized. And you can see the third step, repolarization, normally go deeper than that. Okay, it's deeper, so the one that lower or more negative than the resting membrane potential, that is a hyperpolarized, just more negative than the resting. So at that time, the potassium channel keep on remain open and make extra potassium just flow out. So the inside become more negative than the resting stage. So this is a hyperpolarization, and at this point, the sodium channels start to reset. Reset, we mean the inactive channel, inactive gate is released and active gate get closed. So that is a first step of the action potential. Resting stage with a polarized cell membrane, and then it starts to depolarize, become zero, become positive, and then go back negative stage again, which is repolarized, and go further, that's hyperpolarized. So here, this fourth step, we are only talk about the cell membrane potential. Are they negative or positive? If it's negative, that's polarized. If it's positive, it's a depolarization, and come back to the negative. It's repolarization, and more negative, that's a hyperpolarization. So think about those ion channels open or close at the different stage. What happened, what is the event, and what is the order. So this is a cycle to form an action potential. But remember, so far, what happened is the potassium all go out and the sodium all go in. So which is, although the membrane potential is similar to the resting membrane potential, but so far the ions are not in the right position yet. So at the end, after the hyperpolarization, those sodium potassium pump have to work and reset everything, make those sodium outside the cell and keep a lot of potassium inside the cell. Repolarization just reset the electrical conditions, but the ionic condition, we see the different concentration of different ions outside and inside cell is reset by the sodium potassium pumps. From that point of time, then the cell is reset to the resting cell. It's polarized and have more sodium outside, more potassium inside. And once it's resting, and they are ready to be response to another stimulus to get another action potential. When we talk about action potential, we mention one term, we call it a threshold. The threshold is this dot line here, you see. That dot line is about minus 50, 55, and it's kind of a difference between different cells as well. So that minus 55 millivolt in neurons is a time that if those membrane potential reach that point, all the sodium ion channels will open. So that's a threshold, that is a switch that to activate a positive feedback. Once the positive feedback, nothing can stop it. Okay, so that is a time to fire the axon, to fire the action potentials. Threshold, that's a voltage or membrane potential that which the action potential will trigger. If the membrane potential didn't reach the threshold, like the first two stimuli here, if they didn't reach the threshold, then there's no action potential. And the second part, well, in fact, you see two stimulus just very close to each other, so it kind of form like a wave summation, just like the one you see in the muscle. So these two together push the membrane potential to a certain point and above the threshold. Once it's reached the threshold, then the rest event are exactly the same, no matter which axon they are in. At the threshold, the membranes have been depolarized. Remember, it's always go up to about minus 50, so it's depolarized by about 50 to 20 millivolt. And at that time, the sodium permeability increased, which means the sodium ion channels opened. More sodium ions come in than the potassium ions come out. So that is a time, once you reach the threshold, the positive feedback will begin. Once the positive feedback begins, then nothing can stop it. Therefore, we call the action potential is a all or none. If it reaches the threshold, then it just get all the action potentials like this. And if it doesn't reach the threshold, those two, there's no action potential. So either one action potential, all action potential, or non-action potential. So it never just look like a gradient potential, can be half, can be more. All the action potential, once you get it, it just look like this, no matter where it is. The propagation of action potential just allow the action potential used as the nerve impulse and travel along the axon from the axon helix till the axon terminal here. It's always this direction, and once those action potential reach the axon terminal, it will trigger those neurotransmitter to be released. Think about the neuromuscular junction as an example. Once the action potential reaches the neuromuscular junction, those calcium ions channel open at the axon terminal, and then those small vesicles that contain acetylcholine will released. So that is the event happened at the axon terminal upon receiving action potential. Different axons, different neurons will release different neurotransmitter, but that is the idea. You use the action potential, target, and send to the axon terminals. The propagation of action potential is start from the local current that is caused by the sodium influx. Those local current will cause a depolarization at the nearby area, so that's how those action potential get spread. But that's just a beginning. So once those local current reach a threshold, so those local current will trigger a action potential. So those action potential will propagate away from the origin, and then it reach next point, and as long as the action potential is large enough, it will trigger another action potential, then it relay those signal related to the axon terminal. If an action potential is a start origin from here, origin, and this origin will open those sodium ion channel first. Once those sodium ion channels open and generate action potential, so after those peak, those potential increase. So what happened is those sodium ion channel will be inactive and closed for a while. So that makes sure all those action potential go into one direction, because once they go to further direct, and those new local area like this point cannot send the signal back, because at this location here, the back location, the sodium ion channels are closed. So that makes sure those action potential are propagate in one direction. So the action potential need those active stage sodium ions to generate. So once the action potential is initiated, it will self-propagate itself along the axon. So in the non-myelinate axons, each segment, each susceptive segment have to be depolarized and then repolarized, so that take a very long time. But however, in the myelinate axon, it's different. So let's see the propagation here. It starts from the origin at this location, and what you measured is this point here. Here is a probe. That's your measurement. The origin, the action potential is generated at this location already, so it will move across the axon. And so far, your point of probe didn't receive any signal yet. So the action potential will propagate because localized membrane potential will spread. So just go along those blue line here and across the whole axon. So that part that you measure with the probe here will receive a depolarization. We'll see those membrane potential just rise up. After the action potential passed that point, and your probe will detect that at this localized region, those membrane potential get reduced and hyperpolarized, and then reset to the resting potential. So that is how the action potential is generated and propagate. So during the action potential generate time, as you see in this curve here, at the beginning, at this first part, which we call the absolute refractory period. If it's a refractory, it means it's hard to generate another action potential. Absolute refractory is a time that even the stimulus come in, there's no action potential will be generated, because at this point the sodium ions channel cannot be open more, because either they are in the positive feedback already, or they just cannot open because the inactive gate is closed. And then after the peak, this period, there's another period, we call it a relative refractory period. At that time, those sodium start to reset. Sodium ions start to reset, but however, the ion concentration outside the cell and inside the cell is not reset yet. So during that period, it's hard to make another action potential, but it just make the threshold higher. But in fact, if the stimulus is strong enough, it is possible that we get another action potential within this time with this period of time. And after that's a refractory period, it means the cells are totally reset and they are ready for a brand new action potential to be generated. So the absolute refractory period cannot respond to another stimulus because of sodium ion channels, and also those it also ensure that all the action potential is separate. It's all or none. It won't add two action potential together. And also it enforces the one-way transmission to make sure it will not go back. And the relative refractory period is this period here, and it have a high threshold, and at that time, it's just hard to get action potential, but it's not absolutely not able to. At the end, let's see a few questions. The neurons generally repolarized once the membrane potential reach approximately positive 30 millivolt, because the answer is voltage-gated potassium channels gets open. At that point, the sodium channel closed, but the reason it start to reduce, the reason that action potential start to reduce and hyperpolarized is because the potassium channel open. Next question. In an organism, action potentials are propagated unidirectionally towards the axon ending because the answer is membrane become non-responsive due to the inactive sodium ion channel after action potential generate. So once the action potential go across the axon, so all those events happen is the sodium ions open first, and then they closed. Then the closed stage is inactive, have to wait a while until next time it open. So that makes sure those action potential just travel along the axon in one direction. The last one. You would expect a neuron that depolarized to minus 65 millivolt would minus 65. So think about what is a threshold normally. The answer is return to the resting membrane potential without generating an action potential. So for the threshold is normally minus 55. So at that time point, if it depolarized to minus 65, it didn't reach the threshold yet. So it won't generate action potential. That's why we see none or all. Since it didn't reach, there's no action potential.